Hello everyone. Today we're looking at the problem minimum time to break locks 1, which was question 2 in Biweekly contest 145. So the question reads that Bob is stuck in a dungeon and must break n locks, and each lock requires some amount of energy to break it. The required energy for each lock is stored in an array called strength, which will be given, where strength I indicates the energy required to break the ith lock. So then we're going to go through the following characteristics to break a lock. So we have a sword, which has an initial energy of 0. We also have a factor x, and this x is going to increase the energy of the sword by whatever its value is at every minute. So then to break a lock, the energy of the sword must reach at least that strength, and then once we break that lock, the energy of the sword resets to 0, but our factor x increases, and we're given the value it increases by k. So to reiterate, our energy of the sword starts at 0. Every minute it increases by whatever our current factor is. Whenever we break a lock, we reset our energy to 0, but we can increase our factor by the given value k. So we want to determine the minimum amount of time it takes to break all the locks and escape the dungeon. So looking at the example 3, 4, 1, and our k being 1, we have our output of 4 because it takes 4 minutes at minimum to break out. So we can look at this table to see exactly how this happens. So we start at time 0 with 0 energy, and we can't do anything. So here we just go to the next minute, and you'll see that we're now at time 1, and our energy is now 1. And our energy is 1 because our current factor is 1. So we're going to increase by 1 every minute. So here we could actually break the third lock because it has a value of 1. So what happens here is that we would reset and then update our x. So our x becomes 2 because it was previously 1. Our k value is also 1, so we're going to increase our x by k. So the next minute, our time is 2, our energy is 2, we don't do anything. Then we get to 3. Our energy is 4 at this point, so we could break the second lock with value of 4, and again we increase our factor by k, so now our factor is 3. Then at time 4, our energy is 3. We can break the first lock, and then our factor again is 3. So let's briefly chat about exactly how the factor works. So like we said, our energy starts at 0, and our factor will always start at 1. So let's think how we can use these to determine which locks we can break, or rather, how long it takes to break a lock. So let's say here that we're looking at this lock of 4. So we know our energy is going to start at 0. And let's just write our 4 here so you know what we're breaking. Energy starts at 0, and our factor is 1. So this means we're going to have 0. The next minute we'll go to 1. The next minute we'll go to 2, next to 3, and then next to 4. So we have to do 1, 2, 3, 4 minutes until we can break this lock. Okay, so that makes sense. So let's say now that we increase our factor by our k value too. So this would become a 3. So now let's look, maybe we want to break 5, right? So here what would happen? Well, we would start at 0. We would go up by 3, and then we would go up to 6. And here we're at 6, so we could break this 5. And you'll see there's 2 minutes. So you might notice a pattern here. The time it takes to break is actually equal to the strength, we'll call this S, divided by our factor. But we have to round this up, right? So we could pretty easily find how long it would take us to break a lock by this simple equation here. We could take the strength divided by the factor and just round up to get rid of any decimal point. So now we know how we can determine how long it takes to break a lock, but how do we determine the proper order? Well, this is where it's a bit tricky. You could try a bunch of different greedy approaches, but you'll kind of realize that there's no one way that we could actually always guarantee that we're going to break the locks in the optimal way if we choose greedy. So you might think maybe we always choose the smallest lock, maybe we always choose the largest lock, but you'll see there are test cases that you run into where with both of these strategies, you're going to fail. So another indicator here is that our n value, which is how long that our strengths can be, is less than or equal to 8. And this is a very small value. So when we see something like this, it's a good indication that we're going to do some sort of brute force algorithm. So that's exactly what we're going to do. So what we're going to do is essentially on our first iteration, we're going to go through each one and say we choose to break 2 first. Well, we know how long it takes to break it, right? So we could say I'm going to take my S, 2, divided by the factor, and I know that I will take 2 minutes to break this. So I can choose to do this and then basically recurse on the rest of these. And then what I want to do actually then once I go through all these branches is backtrack. So I'll say, well, I've tried out breaking 2 first, but maybe that's not right. Maybe here I want to try and breaking 5 first. So then I would break 5 first, I would record that many minutes and then recurse through the rest of these options. So really what we're doing here is we're going to backtrack. We're going to try every single combination that we can, and we're just going to keep track of whatever gives us the least amount of minutes. So how are we actually going to do this? Well, you'll notice a couple things. We have to keep track of which elements we're using, right? So say, for example, we choose 2 first, and then we might go into a recursive function here where we, have to do some logic again. Well, we need to know that we previously selected 2. So how can we actually do this? So we could have some external data structure where maybe we have a space for each of the elements in strength and we try to update this, but this is not as elegant. What we can actually do is use a bit mask. So what is a bit mask? So a bit mask is just an integer that we can use in order to keep track of the state of our problem. And I'll show you how this works. So let's say that we decide that we want to break the 0th lock first. So how would we use our bit mask to represent this? Well, you'll see here that we have 1, 2, 3, 4, 5, 6, 7, 8 bits that we could set on this integer. So what we would do in this case is say, well, I want to record that I am breaking the 0th lock here. Then I would start from the right at my 0th bit, and I would set this to 1. Now, essentially, when I go down into my recursive function, I'll have this bit mask available. And what I can say is, as I'm iterating through my strengths, I can say, okay, well, let me check my bit mask and see. Well, I've already done the 0th, so I can't do this. Then I can move on to the first bit, and I'll say, okay, well, I haven't done this one, right? So I could potentially break this one next. And that's how we're going to use our bit mask. We're going to, as we break locks, we're going to set the bit, but then once we go through all our branches, right? Because remember, we're going to try breaking 2 first, but then at the end, we need to get rid of that. So at a certain point, this was 1, we're going to say, well, now we need to revert it back to 0. So really what this bit mask is going to do is it's going to allow us to keep track of the state of our problem at all times by setting bits that we have broken and then unsetting them when we want to go back and try something different. So really, this is the entire algorithm. We're going to just do this brute force algorithm, trying out every single possibility that we can, but also keeping track of the current state of our problem and which locks we've already broken by using a bit mask. So let's hop over into the code and see exactly how this works. So the first thing I want to do here is just keep track of the minimum amount of minutes that we have found so far. So we're going to start this with infinity, and then as we find valid configurations of lock breaking, we can update our minimum value here and finally return this at the end. So the first thing we do here is a slight optimization. Basically what we're saying here is that if we've already found an answer, but what we're currently looking at is going to be greater than the answer we found, there's no point in continuing. Because we know that since we've already found something smaller, if we continue with this path, there's no way that it's ever going to beat this because we're just adding minutes on. So in this case, we're just going to return early because we know that the branch that we're going down is not going to be the optimal solution. Then what we're going to do is we're going to check and see if we're done with the problem. So what we do is we're going to have this C, and this stands for the number of bits that are currently set. And if we go through every bit in strength and we see that they're all set. So for example, if every bit in our integer is 1, this means that we've broken every lock here. So what we can do then is just record our answer. So basically what we're going to do is say, if it's smaller than what we have already, then let's set that as the minimum. Otherwise, just keep our current answer and then return because we've already broken every lock. So we can just go back and try a different path. Then what I'm going to do is I'm going to iterate through all of my strengths. So what I'm going to do here is I'm going to check if this lock has not been broken yet. So what I'm doing is I'm taking that bit mask and I'm checking if that ith bit is equal to 0. And if it is 0, this means that I have not broken that lock yet. So I'm going to do my equation just to get the number of minutes it takes to break that lock. Remember, that is our strength divided by our factor. Then Then we're going to do our recursive call. So our current energy is going to become 0 here, because remember, when we break a lock, our current energy resets to 0. And here is just, we're recording that we've broken that ith lock. We're going to increase our current minutes by whatever m we found up here, and then increase our current factor by k. Then down here, we're just going to call that recursive function. So we're going to pass in 0 for our energy, 0 for our bit mask, 0 for our minutes, and then 1 for our factor. Then at the end, we just return that answer that we found. So let's submit and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe. It really helps the channel, and thank you for watching.